This lesson we are going to work on coordinate proof. In particular, this particular lesson combines some of the things that you've done in pre-algebra and algebra 1. Specifically, with those two classes, you spent a lot of time working in the coordinate plane. And if you go back to our first unit, we also did some work with the coordinate plane, basically to refresh your memory of those things, like we did the midpoint formula, we did the distance formula, we've done some work with slopes and lines. All of those are things that you've covered in earlier classes. We just rehashed them to refresh your memory. This particular lesson is about combining those things that you've done in pre-algebra, algebra 1, and our unit number 1 in geometry, and creating proofs based off of those sets of skills. The two main things that you're going to need to do with that are to be able to position a figure or draw a picture in the coordinate plane that actually fits the situation you're working on, and then use the coordinate plane and distance formula, midpoint formula, all the stuff that we know, use it to write up an explanation why something is true. This process is actually called a coordinate proof. When you use the coordinate plane as a tool to prove something, it's called a coordinate proof. There are, of course, some strategies that you can apply to help make these a little bit simpler and a little bit easier. In particular, using the vertex makes things much simpler. Using the origin as the corner, keeping something in quadrant 1 so that you don't have to mess around with negative numbers, makes it easier. Centering something on the origin, using one of the x and y axes as a side of the figure, they'll all help. For instance here, position a square with side lengths of 6 units in the coordinate plane. Well, again, position just means draw the picture. And since we're working within the coordinate plane, we'll simply say, all right, it's a square with a side length of 6. Then we'll start by putting something on the origin. That's one strategy to help make things easier. Keep it in the first coordinate. We'll make a side length of 6. A side length of 6 using both the x and y axes as sides. And then we'll finish off and draw our square. And that's it. We're done. We've positioned a square. No more. Similarly, position a right triangle with a leg length of 2 and a leg length of 4 in the coordinate plane. Big hint again, use the origin. If we put the origin as one of the side lengths, or one of the vertices, we could draw our right triangle with a leg of 2 and a leg of 4 using the axes as side lengths. Connect our triangle. We're done. We've positioned the triangle in the coordinate plane. Of course, positioning the figure is the first step. Creating the picture so that you can see what's going on is the first step. The second step is to start applying all your previous knowledge. You may need the midpoint formula, slope formula, distance formula, something about segments, something about parallel, perpendicular, and whatever things that we've got. All of our information that we've done before is at our disposal. We'll need to start using them, and basically it's recognizing the earlier information. For instance, show that the triangle of ADB is half the area of triangle ABC. Of course, some relevant information that you're expected to recall. How do you get the area of a triangle? You're expected to remember area of a triangle is 1/2 base times height. So if we are looking at these pieces, we would have to say, figure out the area of triangle ADB, figure out the area of triangle ABC. Well, because it's simpler, triangle ABC, I'm looking at that one, and we can get the area here This one we can simply count 1, 2, 3, 4. That's a base of 4. Likewise, we have a height of 6. So that area would be 1/2 base times height. Half of 4 is 2. 2 times 6 gives us 12 square units. That's one of them. Similarly, we would have to get the area of our second one. Triangle ABD. We need the area of this triangle. And so we would have to note, of course, 1/2 base times height. Well, we know base and height are going to come together at a 90-degree angle. Base and height will either be a T or an L. With this picture, where are the base and height? We could recognize these two components here. We could recognize that this is a 6, that's 2, right along here, 6 and 2. So we would have base times height, which tells us 1 times 6 gives us an area of 6 square units. Finally, to finish it off, our coordinate proof, the area of triangle ADB, that was 12, we figured it out there in the blue, equals half the area, I'm sorry, I had that backwards. Triangle ABD was in the red, not the blue. ABD was 6. And then ABC, that was the bigger one, that was the one in red. Here we go. Since that's true, here's our proof. We're finished. Now, each of those first two examples we did, where we were focused on positioning a figure and where we were focused on proving, both of those had their coordinates based in numbers. They actually had specific things like a side length of 4, a side length of 2, a side length of 6. It had pieces like area based on numbers. Those are all things that you would have worked on with pre-algebra and algebra 1, some types of skills. To meet the high school geometry standards, we expect you will do this same type of thing with variables. Position a figure in the coordinate plane. This one, though, is a rectangle with width of m, and the length is twice the width. Remember, twice the width is simply saying, since the width is m, that's 2 times m. You'll notice these are with variables. To position the figures, we'll still use our coordinate plane. And the key characteristic that we have to observe, if we're looking at a width of m and a length of 2m, we could simply kind of pick and choose. Now, we can't give it a specific number, but we can choose how many tick marks we want to use. We'll still use the origin, but if I come over and use just 2 of these and say this is a length of m, we would note then that this is the coordinate m to the right of 0. To get the length or height, we would need 2m. Well, since I chose to use 2 of the squares, 2 units for m, that would be one of them. Go up again, that would give me 2m, so that's a length of 2m, giving me the coordinates, left and right 0, up 2m. And then we can continue and just draw out the rest of it, getting our rectangle. The coordinates there, m to the right, up 2m, and we're done. We've got it positioned. Once again, I'd like you to notice we're focusing our picture using the origin as a corner, as a vertex, using the x and y axis as much as we can, and staying in the first quarter, staying in the first quadrant. All right, another example of positioning these. Position the figure in the coordinate plane where we have a right triangle, legs are S and T. Well, since we have a right triangle, we'll want to form the right triangle centered on the origin and use the x and y axes to form that right angle. Well, we can simply go through and say, here's my length of S, here's my length T, my length S, so we have legs S and T, and then we'll be able to just come right up and draw them. There's our triangle. Noting, of course, we're using the origin. This would give us T0 for coordinates, and since this was straight up, it would be 0S. Done. One thing, of course, that we should be careful about, so far with every single example that we've done where we were drawing these, where we were positioning the figure, they were right triangles, they were rectangles, so we knew that they had a right angle. That's what allowed us to go through and simply say, because I know that they've got a right angle, I can actually use both the x and the y axes. That's not always going to be possible. It might be that you can use only one of the two and not both. You can only use both when you know that it's a 90-degree angle. For instance here, position is square with side length 4p. Okay, well, since it's a square, we know that a square is actually going to have that 90-degree angle. So we'll use the origin. We'll take advantage of the 90. And then go up. And you'll notice the big reason why I chose to use the grid lines of 4. If I'm going to be using 4p, I want to be able to simply say 1p, 2p, 3p, 4p. 1p, 2p, 3p, 4p. I'm using the grid lines not to count by 1, 2, 3, 4, but instead I'm using the grid lines to count p, 2p, 3p, 4p. That would, of course, then lead us to the coordinates 0, 0, 4p to the right, up 0. Over here, we went left and right 0, up 4p. And then the last one, we'll take our x coordinate below 4p and the y coordinate across 4p, and we're done. Now the last one that we will have is to actually do a proof. And you'll notice the coordinate plane that I have didn't include the second, third, and fourth quadrants like I had before, because for the most part, we want to leave these things in the first quadrant as much as possible. That way we can work with only positive numbers. So here we go. We've got the rectangle PQRS, and just for the sake of completion, we could draw this and say, and my dimensions may not be perfect, P, Q, R, and S. Right, so here's what we've got. We need to prove that these two diagonals are congruent. And this is a piece that's going to play a role connecting to what we actually did in homework 4.7. Remember, in homework 4.7, that one was about CP, more appropriately known as the definition of congruent triangles. In our last lesson, we saw that if you can explain why triangles are congruent using side, 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 side angle, side, or anything, if you can show that triangles actually are congruent, then anything that is a matching pair of sides, any matching pair of angles, will also be congruent. So here's what we would observe. If we want to show that the diagonals are congruent, we could draw this out so that we would have a triangle here, drawn out with the yellow, And we could also have it here with the red. If we are able to show, and if we are able to get triangle PSR, that's the red one, actually congruent to triangle QRS, the yellow one, then those matching diagonals, those corresponding diagonals, will be congruent. So why is it then that the red triangle and the yellow triangle are congruent? Well, to start off with, let's make a couple of observations. PS is going to be congruent to QR. That's our first pair of congruent sides. And that's because we know opposite sides of a rectangle are always congruent. We knew it's a rectangle. Sweet, let's take advantage of the fact that we know it's a rectangle. That's one pair of congruent sides. The left is congruent to the right. Additionally, we would be able to say angle S is congruent to angle R. Why? Why is it that this angle is the same as that one? They're both right angles. We know that all right angles are congruent. That's the right angle theorem. Right? So that would give us a pair of congruent sides, or a pair of congruent angles. Continue it further. Both those triangles share the bottom one. We would have SR congruent to RS, that shared side. Since the shared side forms the symmetric property. Remember, it's the symmetric property because the letters got flipped. SR and RS. If we actually kept the same order, it wouldn't be symmetric property, it would be the reflexive property. So there are three pieces. These three pieces come together and tell us triangle PSR is congruent to triangle QRS, and we used side angle side to do it. That gave us the fact that the two triangles are overall congruent. The red triangle and the yellow triangle are the same. Our last step, since they are the same, those diagonals, PR is congruent to QR, and we know that because the definition of congruent triangles, which we choose to phrase CPCTC, corresponding parts of congruent triangles are congruent. We're done. Now, I would like to point out, with this particular video, we didn't do anything where we used midpoint, and we didn't use the midpoint theorem. We didn't do any examples where we had to calculate a length using the distance formula. One other way that we could have gone through and done this problem, I didn't want to do it this way because this method I think was easier, but we did go through and get first pair of congruent sides. We did go through and get second pair of congruent sides. If we didn't know that this was a rectangle, one thing that we could have gone through and done is use the coordinates of the points, and we could have applied the distance formula and simply immediately in one step, we could have instantly gone to show distance formula, get a number, distance formula, get a number, and then because they are the same length, that would have told us that they are congruent. There are many different correct avenues that you can use when you apply coordinate proof. Use any formula you want. You can use slope, you can use midpoint, you can use distance formula. We didn't go through and do them here, but those are tools that are available to you.